Protons flow back into the matrix through the F1 ATP synthase particle. Here it looks vaguely like the lollipop that we talked about earlier, to relieve the proton gradient. We're going to take a closer look at this last process in just a second. So, we can demonstrate proton pumps. But what are the proton pumps? I alluded to the fact that they're part of the phospholipid protein complexes. This slide illustrates the preparation of synthetic phospholipid bilayers, that is synthetic membranes, in which one of the respiratory complexes was inserted, in this case complex 1. When NADH is added to these membranes as an electron donor, along with the compound X, one of these redox dyes, to accept electrons from the complex, protons were seen to be pumped into the vesicles so that the pH of the solution increased. This shows that complex 1 was not only a redox complex, but a proton pump. These experiments also showed that there were 3 sites of proton pumping, and that these sites, complexes 1 and 4 as well as coenzyme Q, correspond to the 3 steps in electron transport involving large negative standard free energy changes that were originally thought to be actual sites of ATP synthesis. We even know something about the stoichiometry of proton pumping. About 4 protons are pumped across the crystal membrane for every pair of electrons transferred from complex 4, also called cytochrome oxidase, to oxygen. Now, here on the left is an electron micrograph of a single F1 ATP synthase molecule. Let's look at how ATP synthase works. First of all, it's a regulated proton gate, controlling the flow of protons into the mitochondrial matrix from the intermembrane space, or from outside the mitochondrion. Note the multiple polypeptide subunits. Some are embedded in the crystal membrane. These are called the F0 part of the structure. Others make up the lollipop head, the F1 particle facing the mitochondrial matrix that Racker isolated. This head consists of alpha and beta subunits. When there's a lot of ADP around, which would indicate that the cell is rapidly using up ATP, so this is a busy cell, the excess ADP binds to the alpha subunit and opens up the proton gate. So the alpha subunit is a regulatory protein whose shape changes when it binds this excess ADP, opening a pathway for the protons to flow back into the matrix from where they have accumulated during electron transport. When the gate is open, the protons in the intermembrane space of the mitochondrion bind to the A subunit shown in purple here. The C subunit forms a cylinder that can spin like the armature of a motor when protons are passed to them from the A subunit. As the armature spins, protons are ejected into the matrix and ATP is synthesized, as you saw repeated here a few times. The process of active transport that pumps protons, followed by the regulated relief of the proton gradient through a proton gate, is the essence of oxidative phosphorylation. As summarized on this slide, the pumps are coenzyme Q and respiratory complexes 1 and 4, as I mentioned. They are fueled by the negative free energy change of their redox reactions, and the F1 ATP synthase is a regulated proton gate using free energy stored in the proton gradient to make ATP. Think about why these gates are regulated.